Hi everyone, and welcome to this session. Today I'm talking to João Luís Rosa regarding traversable wormholes with double layer thin shells in quadratic gravity. We're going to start from a high level and paint sort of the broad picture of these gravitational theories, and then we're going to dig into the specific wormholes that Joao's been researching. Hope you enjoy it. How about we start with introducing like theories of gravity in general? Like we have, Newton's concept of gravity, and then we have general relativity as well that sort of provides a different formalism. Would you mind providing some background as to what those are, and then also quadratic gravity, which we will come to in the paper, where that sort of sits in this entire discussion?
Yeah, so Newtonian gravity is basically just a specific case of general relativity. So what Einstein did was not to develop a completely new theory. What he did was to extend on theories that already existed. And we can think of Newtonian gravity as being a particular case of general relativity. And specifically, it's a particular case when the strength of the gravitational field is weak. So if you take, for example, the equations of general relativity and you make an approximation for weak gravitational fields, you obtain the equations for Newtonian gravity. So in some sense, Newtonian gravity is included in general relativity. The main difference between the two is that Newtonian gravity assumes that space-time is flat, whereas general relativity assumes that space-time has curvature, and that's where general relativity actually comes from. There is this, I don't know if you remember when you were studying physics, but there is this physical quantity called the action, and all of the physical theories come from the action. So you write your action, and you can apply some methods to obtain the equations of motion from a given theory from the action. And general relativity has the particularity that the action depends on the curvature of spacetime, something that Newtonian gravity doesn't.
Mhm.
Still, general relativity is the simplest possible form of a theory that includes the curvature of spacetime. It's basically linear in the curvature of spacetime. It's just a function of this quantity r that is, it's called the Ricci scalar, but basically it's the curvature of spacetime. And what happens in quadratic gravity is you take an extension. Here it is. Here on this section 2, quadratic
Right.
r plus alpha r squared. So if you just take the r and you discard the alpha r squared, you have basically general relativity. So the action is linear in this quantity, this Ricci scalar that is the curvature of spacetime. So in some sense, quadratic gravity is an extension of general relativity, where you include also quadratic terms in the curvature instead of just the linear ones. And quadratic gravity itself is just a particular case of these things called the f of r theories of gravity, as you see here in action number 1. Where the action actually depends on some arbitrary function of curvature, and if you take this arbitrary function to be quadratic, then you recover quadratic gravity.
Mhm. Okay, I would like to paint some intuition for some of the concepts here. So you mentioned the
Yeah.
action before, and action is S in equation number 1 here.
Yes.
We also have the Lagrangian in here, and maybe a good starting point would be to just describe those two, like how they differ, what the Lagrangian tells us about the system, what the action tells us about the system, and then we can move over to maybe the Ricci scalar after we've talked about
Yeah,
the action
they
and
basically
the
they
Lagrange.
basically have the same information. So the action and the Lagrangian, they both have the same information. They are just equivalent different ways to write the same thing. So if you take the action S and you want to obtain the equations of motion, you apply something called a variational method. And if you have instead the Lagrangian and you want to find the equations of motion, you apply the Euler-Lagrange method. But the results of both of these methods are the same. It's the equations of motion. So they are equivalent ways of taking the equations of motion.
Mhm. Okay,
And in this
and
case, in here there's a difference. So you have this Lagrangian with a small m. This is the Lagrangian that describes matter, because the full Lagrangian of this theory is everything that's between parentheses. So this f of r plus lm. This is the Lagrangian of the theory. And
okay.
we separate it between the geometrical part, which is the f of r, plus the matter part, which is this lm.
Mhm. Okay. If we talk about this f of r part then, so in
Yeah,
general relativity, we would just have the Ricci scalar here, and
yeah.
that tells us something about the curvature of spacetime. Um, could you elaborate on that a little bit? Because I think it's related to the Ricci tensor as well, and sort of the Riemann curvature also of the space ultimately. Could you describe a little bit how we take something, and correct me if I'm wrong here as well, because my understanding right now is that the Riemann curvature is sort of a more elaborate way of describing the curvature of space-time for a given location, let's say. And then with that information, we can somehow condense it in its most important way, I would assume through some form of linearization into one scalar that we can then put into these equations. But maybe that understanding is not correct. Could you elaborate a little bit on where we get the scalar from, what it represents?
Yeah, so it's not really a linearization, but it is, as you said, an adequate, convenient way to contract the Riemann tensor. So the Riemann tensor is a rank 4 tensor. This means that they have 4 different indices. You can imagine it as a 4-dimensional matrix somehow. And but the thing is that not all of the components of this matrix are important to describe spacetime. Only a few of them are. And so what you do to extract the ones that are useful for you is to make what we call contractions. So we sum over some of the components of this matrix to take the Riemann tensor. We make this contraction and you obtain the Ricci tensor, which is only a 2-dimensional. So there's two free indices on this matrix. And then if you want to even further simplify the framework, you take another contraction and you end up with 0 indices, so a scalar that is the Ricci scalar. But basically they have not the same information because the Riemann tensor has the full description of spacetime, but as I said, not all of the components of the Riemann tensor are important for you to analyze what happens to the gravitational field. So you'll make these contractions to extract only the useful ones, and ultimately the useful one is the Ricci scalar.
Mm-hmm. And when we say the curvature of spacetime, is it fair to use our intuition of curvature in general, or sort of a like derivative of a general function? Like if we think about this in 2 dimensions, like just a regular function, one parameter of that function f of x, you
Yeah.
take the derivative of that, that sort of gives you the, well, not the curvature if you will, but if you take the second order derivative, you would get the curvature. Is it kind of the same? Is the same intuition that underlines this?
Yeah, it's basically the same thing. So you basically start with something called the metric, and the metric is basically your gravitational field. It's the thing you call the function f of x, and then you have to take 2 derivatives actually. The first derivative gives you some quantity called the crucible symbols or the connection, and the second derivative or some combination of second derivatives gives you the Riemann tensor. So it's exactly what you're saying. So the Riemann tensor is somehow the second derivative of some quantity that you call the gravitational field.
Right. And this gets me now to the point I really want to ask, which is when you take the second order derivative in a 4-dimensional space, how do you condense that into one scalar? Like, what is it? Is there a conceptual way to thinking about what this represents? Because if you just think about a 3-dimensional function, you could try to express the curvature of that as one number, but you could have a very different curvature if you have, let's say, a saddle point of your 3-dimensional function. You could have a very different curvature in the x dimension compared to the y dimension.
Yes.
Is there a way to conceptually think about what this curvature tells us about spacetime? I know it's in 4 dimensions and also potentially quite hard to understand, but how come we're able to condense that information into one scalar? And what does it represent?
Yeah, so the Riemann tensor conveys all of the information. So all of these derivatives in different directions, and actually, as you said, 4 dimensions, 3 space plus time. The Riemann tensor transports all of that information. But then what happens? Okay, it's a little more fundamental than that. So basically, what Einstein realized is that the uh, if you assume that conservation of energy exists, which is something that we expect from the universe we observe, and you want to relate somehow the distribution of matter with the curvature of spacetime, because that's what general relativity does. It takes some distribution of matter and it associates that distribution with some geometry of spacetime. If you want these two things to happen, so association between geometry and matter is conserved, there is only one possible combination of geometrical quantities that is proportional to the distribution of matter. And this particular combination of geometrical variables. It's called the Einstein's tensor. Usually it's G with 2 indices. This particular combination is made of contractions of the Riemann tensor. So you have the Riemann tensor describing the entire, let's say, the entire geometry of spacetime throughout these derivatives of every direction, and every direction with respect to every direction, basically 4 dimensions with respect to 4 dimensions.
Mm-hmm.
but your theory doesn't need all of these components, because the only possible way to have a direct association between geometry and matter is to extract only a few of those components and these contractions, as I said before. So there's no intuitive way of thinking about this, because, as you said, it's really difficult to imagine derivatives in 4 dimensions. What we need to, in my opinion, what we need to realize is that these particular choice, this particular contraction of components of the Riemann tensor, those are the ones that allow you to find a theory that finds some kind of proportion between geometry and distribution of matter.
Okay, good. So maybe we can get started on the actual topic of the paper, which is
Yeah.
wormholes. And maybe one interesting relationship before we start digging into the wormholes in detail is why the connection between quadratic gravity in particular and wormholes. Is there something that inherently makes us want to consider quadratic gravity in the context of wormholes, or would general relativity be equally applicable in that setting?
Yeah, actually, it's not quadratic gravity that is the answer. It's any, or in principle, any modified theory of gravity can do the trick. General relativity is not able to. I mean, you can find solutions for wormholes in general relativity as well. That's not a problem. The problem is that when there is a direct relationship between, as I said, between geometry of spacetime and distribution of matter, and if you take general relativity as a framework to study the geometry of a wormhole, you find that the corresponding distribution of matter violates some conditions. We call them the energy conditions, that imply that the matter necessary to create a wormhole in general relativity is not physical. And so the only possible way for you to surpass this limitation is to consider modified theories of gravity. Quadratic gravity in particular is just an easy example of a modified theory of gravity, but there are several other theories of gravity that work.
Mm-hmm. Okay, and so it's kind of the rationale is sort of okay. We've proven that there is no So are you saying the motivating factor for considering one of these is that if you consider it under general relativity, you'll get nowhere. Like it's already we're conclusively saying that we're not able to find anything if we consider general relativity as is to be the end all be all when it comes to gravitational theories.
No, that's not exactly what I mean. What I mean is that if you are particularly interested in wormholes, and that's just for wormholes, not for everything else, general relativity works so far perfectly. But just for wormholes, if you consider wormhole spacetimes, you will find that general relativity implies that the distribution of matter is unphysical. It basically has, well, I'm oversimplifying here, but basically, if you take general relativity and you try to construct a wormhole based on general relativity, you will find matter with negative mass somehow, which is something that you don't observe in the universe. So only for wormholes, general relativity has this limitation, and you have to turn into modified theories of gravity. But for every other thing, like for cosmology, for the dynamics of the solar system, all that, general relativity works perfectly. There's no need to recur to modified theories of gravity.
Mm-hmm. Well, I mean, I might be thinking about this incorrectly, and please correct me if I'm being very naive here, but it sounds to me like we're approaching a contradiction, right? Like we're saying, okay, in general relativity, we're not able to describe these constructs, so we're employing, let's say, another theory of gravity to be able to explain them. But that sort of implies that general relativity to begin with is not perfect, and I don't know what the evidence we have for that is at the moment. Maybe you could give a summary of what the shortcomings are of general relativity at the moment. Because if you take the theory, here's what I want to get to. If you take the theory as the theory of gravity, general relativity, that is, and you stumble upon this apparent contradiction, then to me that sounds like a case to be made that traversable wormholes in fact do not exist. So what is it that leads us to say, okay, they potentially do exist, and we should consider a different theory as opposed to saying general relativity is right and they're simply unfeasible constructs?
But that's precisely the point that you're raising now. It's that we don't have any observation that seems to indicate that wormholes exist at all. There's nothing in the universe that resembles a wormhole in any possible situation. So that doesn't mean that general relativity is wrong, because there's no contradictory observation. So if we found wormholes in the universe, and we prove that general relativity cannot explain them, then general relativity has a problem. But
Mhm.
it's actually the other way around. We prove that general relativity doesn't allow for wormholes made of feasible matter to exist, but also you don't find wormholes in the universe, so that seems to be consistent, you know? Now, the
Mhm.
thing is that there are other limitations of general relativity, which is, for example, the fact that for general relativity to work on a cosmological point of view, you have to assume the existence of, for example, dark matter and dark energy, which is something that you don't understand very well fundamentally. And so one of the ways to describe cosmology without having to recur to dark matter and dark energy is to use modified gravity. That's one of the areas of research where modified gravity is important. But
Mhm.
again, it's not a limitation of general relativity. One can solve the problem in two ways. Okay, one can say general relativity is wrong and dark matter and dark energy don't exist, so we have to look for a suitable alternative theory of gravity. Or one can say no, general relativity is correct. We just don't understand yet what dark matter and dark energy is, but we will in the future.
Mhm.
So again, there's no contradiction. There's just two parallel routes to for the truth, but both are equally valid right now. There's no observation that uh, contradicts general relativity.
Mhm. Yeah, that's a good point, and I think that's what I was looking for in terms of rationalization for why we're looking at these modified theories of gravity in this context to begin with. But okay, fine. So we're looking at it through the lens, let's say, of quadratic gravity, and
Yeah.
could we then paint a bit of a picture of what traversable wormholes are, and particularly sort of the um, geometric quantity, or like, how we geometrically envision those to be, like what constraints we're putting on the systems when we're talking about these wormholes, because ultimately that is what leads up to the investigations, I would say, that you've conducted in the paper.
Yeah, so there's two conditions for a wormhole to be traversable. The first condition is that it doesn't have any event horizons. So event horizons is this surface you have on black holes that prevent you. So if you fall inside a black hole, you cannot come back because there is this event horizon thing. It works like a one-directional membrane. So if you move from one side to the other, you cannot move back. The first condition for a wormhole to be traversable is that there are no horizons around the wormhole to allow you for moving inside and outside on both directions, actually. The second condition is it's called the flaring out condition, and that's the one that causes problems in general relativity. That is, it's a purely geometrical condition that says that the interior of the wormhole attains the minimum radius. So if you are moving, you've probably seen this image where the wormhole looks more or less like this. The flaring out
Uh-huh.
condition says that the space-time, when the space-time is from both sides is going closer and closer to the center, there is some point here where they attain a minimum distance and then they flare out. That's why it's
Mhm.
called the flaring out condition. So if your wormhole flares out and there is this minimum distance, finite minimum distance between inside the tunnel, it allows for someone to pass through in the center. So if the wormhole satisfies these two conditions, we in our paper we state that the wormhole is traversable, and those are the only two conditions we are looking into. But there's more. If you want to make the wormhole as realistic as possible, you can go even further. You can say, for example, okay, the wormhole might not have event horizons and might have this finite region where something can traverse. But if the tidal forces are too strong, it's not traversable anyway. So you can go to more complicated scenarios, but for us in our paper, we just take these two as conditions for traversability: no horizons and flaring out.
Mhm. Okay, and so when we're talking about the flaring out condition, are you saying that you're imposing some restriction on the diameter of that of the throat of the wormhole, or what is exactly the condition? So fine, you have this flaring out structure,
Yeah.
let's say, but what is the actual condition that we impose
Yeah,
related to
so
this?
if you scroll down, I think there is somewhere, yeah, on the second half of this paragraph, you see, second, the wormhole spacetime has to satisfy the flaring out condition. So this is a geometric condition that must be imposed at the wormhole throat being the place where the radius is minimum. And this function b that's called the shape function of the wormhole must satisfy some boundary condition, which is the one you see immediately after, B of at the radius of the throat must be equals to the radius of the throat, and also the derivative must be smaller than 1. So this guarantees that the derivative part guarantees that the tunnel opens on the other side as well. So it's a condition, it's a geometrical condition, but not only on the function, but also the derivative of the function that describes the spacetime.
Uh-huh. Okay, cool. So you have these conditions, and then there are some different potential solutions to these kind of wormholes. Like, did you have an idea going into what you were looking for? So I know, for example, like I'm gonna butcher this name, but like Schwarzschild wormholes, for example, like Morris Thorne wormholes, for example, or is another example. Do you have some like? Did you have some idea of what you were looking for approaching
So
these
the
investigations?
main idea was that we already know what kind of shape functions allow for these conditions to be immediately satisfied.
Mhm.
So if you scroll down a little bit, there's going to be an assumption for this shape function, some b of r equals something somewhere. But basically, we already know what the geometry of the spacetime must look like, both to avoid event horizons and also to guarantee that the flaring out condition is met. So the idea of this paper is not to find what a wormhole solution looks like in this theory, but instead, we already know what the wormhole should look like. We want to check if a wormhole in this theory is doable with matter with physical matter, because that's the
Mhm.
problem in general relativity. If you try to use this geometry, you find matter that is unphysical with negative mass. What we wanted to check is if you take the wormhole geometry that you know what it looks like, if you take that geometry into this theory, what do you find? Do you also find matter that is unphysical, or are there some particular cases for which you find matter that is physical? And
Mhm.
that's the objective of the paper.
Mhm. And the way you practically go about checking that is you have these different, let's say, patches, and then you have boundary conditions where they are connected, and you want to make sure that they are all satisfied under the confines of the theory. Is that the
That's one
particular
of the
approach?
things. So the thing is that when we did the analysis, we verified that very close to the wormhole throat, matter is physical. So we solved the problem that general relativity had. But if you move too far from the throat, matter becomes unphysical again. And I think this figure two, if you scroll up a little, that's exactly what figure two shows. Yeah. So as you can see, on the left side of figure two, close to r equals 2, yeah, there is this exactly where you have the mouse. So there is this small region where these two functions are positive. So this is the combination of the energy density plus the radial pressure and plus the transverse pressure. And for matter to be physical, you need these two functions to be positive.
Mhm.
And what this figure shows is that very close to the wormhole throat, it's true that these two functions are positive. So it's true that matter is physical. But if you move too far from the throat, these two functions become negative, which implies that, well, matter is unphysical a few some distance away from the throat.
Mhm.
So we solve the problem at the throat, but the problem appears somewhere else. And that's what motivates the second part of the work, where we use, as you said, these junction conditions, where we have to match two different spacetimes. So the idea is, okay, we found a solution for a wormhole that is made of physical matter up to a certain radius. So what if we somehow remove all the matter from the outside of this radius where matter becomes unphysical, and you try to find a solution for a wormhole that looks precisely like the one we found in the region where matter is physical and it's vacuum on the outside of that. And to do this, so to match this interior wormhole solution with an exterior vacuum, we need to match these two solutions, vacuum and the wormhole. Now, the thing
Mhm.
is that because the equations of general relativity and because the equations of quadratic gravity are very, very complicated and nonlinear, it's very difficult to find solutions. So you can find a solution in some region and another solution in a different region, but that doesn't guarantee that the combination of these two solutions is still a solution. So we need these so-called junction conditions, and we need to satisfy these junction conditions in order to guarantee that the matching between these two independent solutions, vacuum and the wormhole, the union of these two solutions itself is a solution of the field equations, and that's what motivates the second part of the paper.
Mhm. Okay. How do you derive those junction conditions? And in particular, the number of them? Like, is the number inherently linked to the geometry of the wormhole that you're proposing, or is it something else that primarily
No,
dictates
it's
that?
only the number of conditions is a function only of the theory you use as framework. So if you take, for example, general relativity, you'll find two junction conditions. They basically say that the gravitational potential must be continuous, must be a continuous function, and the curvature of the surface that separates the interior and the exterior region must satisfy some properties, but there's basically two conditions that you must satisfy. In quadratic gravity, or in general in modified theories of gravity, you may have additional conditions because the equations are more complicated. So to find these conditions, you basically have to guarantee that the equations of motion, so the field equations, the equations for the gravitational field, you must guarantee that these equations are regular everywhere. And the more complicated the field equations are, the more conditions you will have to guarantee that the equations are regular. In general relativity, you need two. In here, you need a few more, but that's basically it. It comes from the theory itself, not from the geometry of spacetime.
Mhm. Okay. Can we also talk a little bit about the geometry that you're proposing? So it's a double shell or double thin shell wormhole. Could you paint a picture of what that means and also why that is the natural thing to consider in this case?
It's not like it's the natural thing to consider in this case. It's more like it's the only way to find a solution that doesn't require unphysical matter. So we can think of this in two steps. First step, you apply the theory to find a wormhole solution, and you can two things can happen, or actually three things can happen. Thing number one is that you still need unphysical matter, so you immediately discard the theory. Thing number
Mhm.
two is that you find some solution that doesn't require unphysical matter at all. And that's what happens, for example, in other theories of gravity, F of RT theory, and etc. There's a couple of papers recently showing that this happens. Or the third thing that can happen is that is exactly what happens here. In some region, the matter is physical, but in some other region, the matter is unphysical. So if you are
Mhm.
more or less lucky to find a solution that satisfies this property, then you need to find a way to remove the unphysical part somehow. And that's where the junction conditions come in. Now,
Mhm.
the thin shell wormhole is, you can think of it as an approximation because in the universe there are no thin shells, but the thin shell, you can think of it, for example, as the crust of the Earth. So the Earth is really big and the crust is a few kilometers thick. So
Mhm.
in comparison to the size of the Earth, the crust is very thin. So you can approximate the thickness of the crust to be very close to zero. That would be the same thing happening here. So you have a wormhole, and of course, thin shells don't exist. There should be some thickness in this shell that divides the interior from the exterior spacetime. But the thickness of this shell is so small compared to the size of the wormhole that we just approximate it to be of zero thickness.
Mhm.
And so you can imagine this wormhole as being some sphere, and inside this sphere there is the throat that serves as a tunnel to move from one side to the other. And around this throat you have a sphere of matter, and this sphere of matter is separated from the exterior vacuum by some shell of matter similar to the crust of the Earth.
Could you say that again? So I didn't quite get it. Like you're saying that we're thinking of it as a sphere with a tunnel inside of it, or
Yes, exactly. It's difficult to visualize this as we speak because of the four dimensions.
right?
But you can imagine it as having a sphere, and inside this sphere there is some finite radius of a tunnel. So you go inside the sphere and you come out on a sphere that looks exactly like this, but on a different place.
Mhm. Okay, okay. And when we're talking about the thin shell, that is for the sphere itself, or it's for the tunnel, or both?
It's on the outside of the sphere. So if you imagine this from the interior to the exterior, you have on the smallest radius you have the tunnel, so the throat of the wormhole. In between the throat of the wormhole and the shell, you have a layer of fluid, and that's also a spherical symmetry, but slightly bigger. And then separating the boundary of this fluid from the vacuum spacetime that's outside, you have a thin shell of also of fluid, but with a different density. So it's pretty much like imagine the Earth, but instead of a core, you had a tunnel, and it's
Mhm.
basically the same geometry.
Okay. Okay. And what is the double layer concept here? So we're talking about this in the context of, let's say, one thin shell of the sphere, but we're saying that we have double layer thin shells in these kind of
Exactly.
solutions.
So this is a very recent and still debatable concept. So in general relativity, this application of the junction conditions to find the matching between for example, some interior and exterior spacetime as we do, two things can happen. Either the two spacetime solutions they match together very easily, and you find that the gravitational field not only is continuous, but it's also differentiable or smooth, as you wanna say. In that case, no thin shell is necessary on the spacetime. But another thing can happen, and the other thing that can happen is that the gravitational field is continuous, but it's not differentiable at the boundary. And when this happens, you need this thin shell of matter to guarantee that this discontinuity in the gravitational field is caused by some additional distribution of matter that's in the separation between the two spacetimes. Now, and this is true for general relativity and for several other theories of gravity. Now, what happens in quadratic gravity, and that's why we are using quadratic gravity in this paper, because if you use um, a more complicated form of the f of r theory, this doesn't happen. It must be quadratic for this to happen. If you consider a theory of gravity that is quadratic in the Ricci scalar, or quadratic in the space-time curvature, you will find that the junction conditions allow not only for these two possibilities, so smooth matching or a matching with a thin shell, they allow for one additional possibility, that is the matching with a double gravitational layer. So the double gravitational layer, it's not very well understood at the moment. We hope that in the future this will make more sense, but unfortunately, as of today, I don't have a conclusive answer for you. But
Mhm.
basically, the double gravitational layer is an additional distribution of matter with some weird behavior that populates the same region of space as a thin shell. So not only you have the fluid inside and the shell separating the fluid from the exterior vacuum, there is an additional distribution of matter with very weird properties that populates the same region of the thin shell and also allows you to make the matching work. Now, if you ask me,
Mhm.
for example, what is this double layer made of? There's no answer for that yet. That's still a topic of discussion, a very active topic of discussion, actually, recently. And the only thing we know is that there are some weird gravitational effects happening in this region. So, for example, we know that in electromagnetism, for example, you have something called dipoles because you have positive electric charges, negative electric charges. You can combine the two to create dipoles, but that doesn't exist in gravity because gravity doesn't have positive and negative charges. They only have mass, and mass is positive. Nevertheless, what we observe is that there's some behavior in this matter that populates the double gravitational layer that seems to work in the same way as a dipole. So it's like you have some electric effects on the gravitational fields that are not very well understood. So unfortunately, we don't have a conclusive answer right now as of
Mhm.
what kind of matter populates the double layer.
Okay. Do we have any indication if it's physical to begin with? So we were talking before about non-physical matter and how you don't want that to be part of the solution. Do we have, let's say, something conclusive indicating that we might not know exactly what this is, and it might have very exotic properties, but nevertheless we know that it is physical matter, let's say.
Yes, so there are four. There's more, but basically the easiest ones. There's four of these conditions that I mentioned before, called the energy conditions, and these are the conditions that you have to verify in order to assess if the matter distribution is physical or not. The first of these conditions, or the first two of these conditions, they state that when you observe this kind of distribution of matter, you must see a positive average energy density. The third of these conditions states that gravitational must be an attractive force, and the fourth of these conditions says that the speed of sounds in the fluid or in the distribution of matter must not surpass the speed of light. So if your matter distribution satisfies these four conditions, you state that the matter distribution is physical, or in general, it is acceptable as a physical matter distribution. Now, how do you assess this? You have, so as I mentioned before, in the equations of motion or in the field equations for general relativity and the same for modified theories of gravity, there is some quantity that describes the distribution of matter. So you can analyze this quantity that describes the distribution of matter, and you can assess if this quantity satisfies these conditions or not. Now, when you make these kind of junctions and you find not only the fluid distribution but also the thin shell and the double gravitational layer, the same analysis can be done. So you can do this analysis for the distribution of fluid. You can do this analysis for the fluid in the layers, and you can do this analysis also for the double gravitational layer. And then what can happen, and that's exactly what happens in our paper, is that some portions of the matter satisfy the conditions. For example, the fluid and the thin shell, if I'm not mistaken, the fluid and the thin shell in this paper, they all satisfy the energy conditions, so the matter is feasible. The double gravitational layer, if I remember correctly, we found that one of the energy conditions is violated, which seems to indicate that this distribution in particular is non-physical. But then again, we go back to the same thing. So we tried to do this in general relativity, and we found that matter is non-physical. We moved into modified theories of gravity. In modified theories of gravity, we found that some matter is physical, but other distributions of matter might not be physical. So we move to different theories of gravity and on and on and on until we find, for example, this one. So in this one, all distribution of matter is physical except the double gravitational layer. So where do we go from here? Well, this is an example that wormholes made of this kind of distribution of matter exist. So now we would have to analyze more cases and more possibilities for the distribution of matter until eventually, and if successful, we would find a distribution of matter for which even the double gravitational layer satisfies the energy condition. So we can think of the work that's published here as a first step. So we prove that it's possible to create these kind of wormholes in quadratic gravity, but we still have a problem. Even though we can do it, we still have a problem, that is the double gravitational layer not being a physical distribution of matter. And that's where we need to go from there.
When we say that it's non-physical, the distribution of matter, is that analogous to saying that it's exotic? So exotic is the term that I've come across when I'm looking into this. Is that analogous to non-physical?
Yes, to a certain extent, because, for example, there are a few known physical scenarios for which matter still violates the null energy condition. One of those is the Casimir effect. And I don't know this very well because this is more quantum related, not gravitational related. But basically, there are a few physical situations for which the distribution of matter might violate the energy conditions. So in that sense, matter is exotic, but not unphysical. But in general, the two are used as equivalent. So when I, in this paper, when I say exotic matter, I mean unphysical matter.
Okay. The other point that you touched upon that I want to get back to as well is you said that the gravitational field would have a discontinuity or at least be non-differentiable. What does that mean from a conceptual point of view? Is that something we observe already in the universe, that discontinuities in this field, or non-differentiability at least of this field? I don't recall which term you used. But do we observe that first of all, and what would that correspond to?
No, we don't observe that, and that's precisely why we need the junction condition. So we always know that the gravitational field must be a continuous function. That's guaranteed, and that's precisely what the first junction condition tells us. So if we want to match these two spacetimes into a single solution for the spacetime, we need to satisfy the first junction condition, which is guaranteeing that the gravitational field is a continuous function. Now, about discontinuities, we do not observe discontinuities in the gravitational field. So the gravitational field changes when you change the distribution of matter. So anytime that the gravitational field varies, this means that there is some kind of distribution of matter in the region where you are feeling this change on the gravitational field. Now, why is the gravitational field non-differentiable here? It's precisely because of the approximation we are making. So if we had, instead of a thin shell, if we had a shell with a specific, with some finite thickness, the gravitational field would be continuous and differentiable throughout the entire spacetime. But given that we are making this approximation that there is a finite a shell with zero thickness between these two spacetimes, and because this shell is made of matter, we find that there is this discontinuity in the gravitational field. But that's just an approximation. It's not something that you observe.
Mm-hmm. Okay. One thing I want to have a closer look at as well is when we set up the conditions here for quadratic gravity, we use the term or the coupling constant alpha. So we have it here in the FOR function, which somehow tells us, well, what does the coupling constant tell us? If you start there, maybe.
So the idea is that you can have as many extensions of general relativity as you want, and these extensions they don't have to be of a fixed intensity. So this coupling constant alpha allows you to measure what's the deviation from your function to general relativity. So if you choose, for example, an alpha that's very, very small, you're basically saying that your theory looks like GR, but has some slight deviation. And if you choose alpha to be really, really large, you're saying that, okay, this is GR plus a big deviation caused by the quadratic term. So it's just a way for you to measure how close to general relativity your theory is, or how far it is from general relativity. Now, the thing is that when you test modified theories of gravity with experiments, what you usually do is to impose a constraint on this kind of coupling constants, because the bigger the value of these constants, the bigger are the deviations you would observe on your experiments because of the additional terms in the action, or the additional terms in the field equations. So when you are making experiments to test, for example, the solar system dynamics, or cosmology, or whatever you want to experiment on, you expect the solutions to be very close to general relativity, because general relativity so far has been nearly perfect in explaining all the observed phenomena. So your theory cannot deviate too much from general relativity, otherwise it becomes uncompatible with the experiment. So usually there is a maximum value, a maximum possible value that these kind of coupling constants are allowed to have in order to still be consistent with experiments.
Right. And that brings me to the follow-up question, which is what I really want to ask, is if we look at the results, or the figures at least that you've put together for this paper, we have a specific value for alpha. I believe it's like point, let's see, 013 here.
Yeah.
When we select something like this, what is that motivated by? So fine, we have some upper bound for what we can allow alpha to be, but I would expect that the solutions here are highly dependent on the parameterization of the quadratic spacetime that we, or quadratic gravity that we select for ourselves. How do you arrive at this value, and is there any, let's say, experimental indication that if quadratic gravity would exist, that this would be a reasonable value? Like, how do you approach that?
Okay, so in this paper, the value chosen for alpha is just, it's not related to experiment. It's just related to the approach we have on the paper. So we need this value of alpha in order to guarantee that matter is physical close to the wormhole throat. So as you can see, the deviation between general relativity and our result doesn't have to be very big, and it's still enough to produce a wormhole that doesn't need unphysical matter close to the throat. So this is where this value comes from.
Okay, so it's like, if I can just interrupt there, it's like
Yeah.
the lower bound for where this occurs. Like you pick
It's
the
not
alpha that's more or less.
it's not necessarily a bound, because we haven't tested what happens in values smaller than that. We have just chosen a few values, and
Yeah.
from the values we have chosen, we realized that this one was the smallest one that allows for this to happen. So it's not exactly a bound, because we haven't tested if it's possible with a value lower than that. But this is one of the values that work.
Okay, but it's not the smallest value. It's not the smallest value in the set, or did you have something that was smaller as well? Like, is it potentially close to a lower bound, or is it just some arbitrary, like, is it the smallest value you tested and it could be arbitrarily low? This,
Yes, no, we don't know if it could be arbitrarily low, so probably not, because again, if you go to alpha equals 0, you recover general relativity, and you know that in general relativity, wormholes are not possible to build without with no physical matter. So certainly alpha cannot go as far as to or as small as 0. In principle, you can have very small values of alpha as long as uh, the remaining parameters counterbalance the value of alpha. Now the thing is that the smaller the value of alpha, we expect that the smaller that this is directly related with the size of the region where matter is physical. So if you choose an alpha that's very small, this implies that the region where matter is physical is also very small. On the other hand, if you take alpha that's too big, you probably increase the region where matter is physical. The problem is that you cannot increase alpha arbitrarily, because if you do that, it becomes incompatible with other types of experiments like in cosmology or the solar system dynamics. So in this paper, we just thought, okay, let's take a very small value of alpha, small enough for it to not affect the compatibility of the theory with solar system dynamics and stuff like that, but still big enough to produce a region where matter is physical close to the wormhole throat, so that we can apply the methods.
Mm-hmm. Do you have a sense of where that starts to become a problem? So let's say we would increase alpha, like how well within the bounds are we, roughly speaking, before we start to deviate too
I don't
much?
know what is the upper bound on alpha. I think it's been calculated from the experiments with solar system dynamics, but I don't know by heart what value is
Okay.
the upper boundary.
Okay, cool. Maybe we can talk a little bit about both the results. I know we've touched upon them briefly already, but then also next steps for the associated research. So, would you mind summarizing the results if there are any points to it that we haven't already covered? Any key takeaways from the investigation you did?
I think we mentioned nearly everything. So the idea is that the goal of the paper was to check if in this theory it would be possible to find wormhole solutions that not only have the necessary geometry but also do not require unphysical matter. And we succeeded in half of the task, because, as I said, the double gravitational layer is still unphysical. So next steps would be, first of all, one could try to change or to play a little with the parameters, the free parameters of the theory here, and try to find some combination of parameters that satisfy all the energy conditions, or all types of matter distributions satisfy all the energy conditions. That would be a successful result, as long as alpha is not too big as to be incompatible with other experiments. Um, Other ways to go would be, okay, now we proved that this is possible to do in modified theory of gravity, or in particular in quadratic gravity, but there are several hundreds of other types of modified gravity where one could apply the same methods and try to extract similar results. So one can also take this paper as an inspiration and try to apply the methods to other theories of gravity, and hopefully find one where all of the energy conditions are satisfied, and wormholes can exist peacefully with the distribution of matter.
So if we
Yeah,
think about the first, if I can just jump in there for a second, if we
yeah.
think about the first proposal that you made out, like playing around with the parameters to see if we can find any other solutions, what beyond alpha do we have to work with there? Like, do we have any other parameters that we can modify and which have a reasonable chance of significantly altering the solutions?
Yeah, so there's quite a few parameters, free parameters here in this model. So there is alpha that controls the coupling with the quadratic term, but there's also the radius of the wormhole throat. So we chose, as you can see here on the caption of Figure 1, we chose R0 equals 2m. So the throat of our wormhole is very close to the radius at which eventually you can have a black hole. So it's a very small wormhole, but you can have radius of the throat as big as you want, as 10 m, 1,000 m, a million m. There's no limit on the size of the wormhole throat. So you can go to other values. And also there is this constant here, this zeta 0 equals minus 60. This is a parameter of the gravitational field, and as long as this value, let me remember exactly because this paper has been a while ago. There are some boundaries on this value, but it's very broad. So I think we choose minus 60 here just because it works. There's no motivation behind this value, but there's a wide range of possible values that still produce suitable solutions. So one can play with these three parameters and try to find a solution that works. Um, we didn't we didn't explore the full potential of the parameters. We just wanted to prove that it was possible for a given combination of parameters. That's what we did, but we didn't go to a detailed analysis of the whole parameter space and to check if some particular combination works. But it could be done.
Mhm. Okay. Very concretely then, like well, for you, in terms of research that you would like to conduct in the same sphere, is there anything after having done this that you think would be like promising enough to investigate? You're saying, for example, you could move to other theories of gravity. Do you have some concrete example for what would be another reasonable candidate that you would look at, or another direction altogether that you would like to take?
Yeah, so after this paper, more recently, I've worked with two students, one bachelor student and one master student, where we did a similar analysis into other theories of gravity. So there is this. I think it was proposed quite recently, and by quite recently, I mean like 2015 or so. A new class of theories of gravity was proposed. It's called the theories where um, there is a specific name for this kind of, yeah. So yeah, okay, for theories with non-minimal geometry matter coupling. So these are much more complicated theories of gravity for which not only the geometry depends on the distribution of matter, but the distribution of matter depends on itself. It's something very exotic and very complicated. Um, but we took two particular uh, two particular theories belonging to this class of theories. One with my bachelor student in Estonia, and another one with my master student in Portugal. And we have proven that for these two theories, it's possible to have wormhole solutions that satisfy all the energy conditions everywhere, and you don't even need to use junction conditions. You immediately find solutions that are made of physical matter, and you don't have any problems there. So if one is looking for suitable theories of gravity for which wormholes are not at all a problem, I would say that this specific class of theories where there's this non-minimal coupling between matter and geometry, this seems to be the way to go right now.
Mhm. Okay, great. We should start wrapping up, but just before we do, I would just like to ask if there are any final remarks from your side, any, let's say, urges or anything you would like to ask to the wider research community, anything of this sort.
Well, there is actually two things, if you allow me. The first one is that I see a lot of research on wormholes, and as a referee for different journals, I get frequently papers on wormholes to revise and to provide feedback and whatsoever. And it's two things are very frequent when one is working with wormholes or working with junction conditions. The first one is that people try to publish papers on wormholes that don't address the problem. So it's very frequent for a person just to find a wormhole solution in a given modified theory of gravity and not make an analysis on the types of distribution of matter. So even if the matter is unphysical and the solution they propose doesn't solve any problem regarding wormhole physics, they still try to publish the work, and I think that's very counterproductive. So if you are exploring wormhole solutions, you should at least check if the matter distribution is physical, because if it's not, you're basically saying that your paper doesn't solve the problem it proposed to. And the second thing is that these junction conditions, they have been mostly they have been worked out in general relativity, but very few works using junction conditions on modified theories of gravity exist so far. It's a growing field actually right now, and unfortunately, many researchers are not aware that the junction conditions are theory dependent, which means that some people are working in modified theories of gravity, but they use the junction conditions of general relativity, which is incorrect. And so I would also call the attention of people using junction conditions, not only for wormhole spacetimes, but also for other types of exotic compact objects or cosmology or whatever suits the person working. If they are working with junction conditions, it's really important to verify which are the junction conditions on the theory being used as framework, because certainly, or in general, they would be different from general relativity.
Mm-hmm. Great. Then let's wrap it up here. Thank you very much for joining. It's been a pleasure.
Thank you very much.
And yeah, great.